This is GCSE Chemistry teaching demo, and my name is Jae Hyun. Let's start with Chapter 2, and these are the learning objectives. Understand what element, compound, mixture are. Understand that pure substance has a fixed melting point and boiling point, but mixture doesn't. It keeps changing. Experimental techniques for separation of mixtures. There's 5 of them in the textbook. Understand how a chromatogram provides information about the composition of a mixture. Understand how to calculate RF to identify the components in a mixture. And investigate paper chromatography using ink and food colorings. Elements are substances that can't be split into anything simpler by chemical means. Okay, elements contain only one type of atom. This is a pure magnesium, pure oxygen, and pure diamond. These are all elements because they are pure, only one type of atom. Another important definition is that it can't be split into anything simpler. Okay? It's pure, but it can't be split into anything simpler. That means you can't just take out one circle, one atom from oxygen gas. Usually there's 2 of them. I mean, in all cases there's 2 of them put together. But you can't just take oxygen, one single oxygen atom, and say that's an element. No, it cannot exist in nature by itself. In nature, this two pair, these are the smallest unit that can exist by itself. Same thing for metal. You can't just take out one atom and say that's a element. Metal usually exists as a metallic bond, so it usually exists like this. Same thing for carbon. 2 important facts: it needs to have only one type of atom, it needs to be pure. And second, you need to identify how it exists in nature. Oxygen usually exists as O2, diamond as just carbon atom just connecting with each other indefinitely. Same thing for magnesium. Okay. Compounds are formed when 2 or more elements chemically combine. There's usually 2 or more different atoms. Water is formed by hydrogen, hydrogen and oxygen put together. Silicon dioxide, silicon plus oxygen. Sodium chloride, sodium plus chlorine. They always combine in fixed proportions and they're always bonded together. Okay. While in a mixture, various substances are mixed together and no chemical reaction occurs. Mixtures can only be separated by physical means. Here, it's a mixture of elements. The yellow, probably I will say nitrogen, and the blue, I will say oxygen. There's nitrogen element and oxygen. So you can't say this is compound. Some people say this is compound because there's oxygen and nitrogen atom, but that's not true. Nitrogen, it's pure, it's element. Oxygen, it's pure, it's element. You need to look at this individual molecules to see if it's a mixture, compound, or element. These this is simply 2 elements mixed together. It's a mixture of 2 elements, nitrogen and oxygen. Here, each molecule has 2 different atoms, so this is a compound, this is a compound. It's a mixture of 2 different compounds. Okay, so it's a mixture and it's also compounds. And here I see elements and I also see compounds. It's a mixture of this element and mixture of this compound. Moving on, mixtures can be separated by physical means. For example, magnet. Using magnet, you can take out metal from non-metal. And if you use melting point and boiling point, If you use boiling point, you can take out saline water, you can take out water. Okay? If you boil a saline water, water will evaporate and you will be left with crystallized salts. And if you use melting point, you can use produce metal. So producing metal means taking out impurities from the metal. And if you use the melting point, you can take out the impurities because all the different types of elements and compounds, they have different melting points. So by fixing the temperature at a specific temperature, you can separate those impurities. Another thing about melting point and boiling point, the presence of impurities lowers the melting point of a substance and raises the boiling point. Okay, memorize this. Okay, solve a few problems in the textbook. For instance, dissolving 10 grams of common salt in 1 liter of water lowers the melting point to about negative zero point 0.6 and raises the boiling point to 100.2. If it's a pure water, melting point is at 0 Celsius, boiling point at 100 Celsius. But if you add impurities, melting points it gets lower, boiling point it gets higher. So let's say a water, you thought it was a pure water, and it starts to boil at 103 degrees Celsius, you know that it's very impure because it's not at 100 degrees Celsius. The melting point can be very useful in determining whether or not a substance is pure, like what I just said. Okay, filtration is one technique for separating a mixture. As you can remember, mixtures, they're not chemically bonded together, they're physically bonded together. So they need to be separated using physical means. Okay. So, quick question, what does chemical means? Chemical means you're cutting this bond. You're cutting this bond. You're cutting this bond inside the molecule. If you cut this bond inside the molecule, you're fundament you're fundamentally changing the identity of the molecule. You're basically changing the, say, carbon dioxide to oxygen. You're changing water into hydrogen. You're fundamentally changing the identity of each molecule. But if you're just using physical means to separate mixture, you're not changing the fundamental structure of carbon dioxide. You're not changing the identity of water. You're just simply separating them to have pure water and pure carbon dioxide. Okay, so that's the difference between chemical and physical means. Now, filtration, it's separating the mixture, meaning it's a physical means. Okay, filter paper relies on the particle size. If the particle size is big, it's going to be filtered. If the size is small, it's going to go through. For example, it can separate a mixture of sand and water. If it's if the sand gets filtered and water goes through, and we say the sand is residue and water is filtrate. And another method, another technique that can separate mixtures, it's crystallization. You remember saline water? When you start to heat it up and it boils and it evaporates, you're left with solid salts, the crystallized salts. This is another way of doing a physical separation. Okay, let's read through this. This is about separating pure salt from rock salt, and we use filtration and crystallization. Rock salt consists of salt contaminated by various impurities, and these impurities are insoluble in water. If you crush the rock salt and mix it with hot water, the salt dissolves, but the impurities don't. The impurities can be filtered off and remain on the filter paper. The filter is then a salt solution. The solid salt can be obtained from the solution by crystallization. So the impurities, they can't pass through this filter paper, but the salt and water, they pass through the filter paper. So that filtrate, you can use crystallization. You can add heat to separate water from salt. And now you have that pure salt on your beaker. Let's go through the last sentence. This is typical of the way you can separate any mixture of two solids, one of which is soluble in water and one of which isn't. Now, distillation. Okay. This is the graph of a distillation. It's basically a similar concept of crystallization, but in this case, it's more about focusing on the gas part. Figure 2.9, distilling pure water from sodium chloride solution. Okay, this is our solution, and we're trying to get pure water. Before, we were trying to get the salt that's left over, but now we're trying to get the water. So what needs to happen is we need to still, same thing, we need to evaporate the water, but we need to condense the water back to liquid form to get the water back. Okay, so what happens here is there's a source of heat, and here there's a source of cooling. It's gas, and we can't collect gas of water. We can't collect the steam. We need to collect the liquid water. So it these so you see the top half and second half, and you see the tunnel. The top half and second half and tunnel, they are separated. It's basically like a straw, like two spaces of straw. So water goes in and takes the heat away from steam, and water goes out. It doesn't touch the steam. It doesn't there's a separate entrance for the cooling water and the steam. Okay, so the water goes in and water cools the steam and it goes out. And the steam gets cooled, so it becomes water. It's condensed, now it drops. And by droplets, you can collect the pure water. Okay. So this is simple distillation. Simple distillation can be used to separate the components of a solution. Okay. So it's a solution. Usually, you only have one solvent, one liquid, and once you get that one liquid out, you can get the rest of the components in the beaker. Fractional distillation is a little bit more complex. It's used to separate a mixture of liquids. Now, it's not just one liquid from simple distillation, it's two or more liquids, such as ethanol and water. For example, separating petroleum, there's different types of petroleum. You use distillation. There's different types of, um, it's a mixture petroleum. And you're going to separate using the boiling points and usually boiling points. Now, this is the graph of a fractional distillation. It's a little bit more complex, but the the idea is the same. The only thing that's different is that there is a fractioning column, and this is to facilitate the separation of different liquids at different boiling points. Okay, so this is about separating water and ethanol. In the end, water has higher boiling point of 100, ethanol at 78. And this is heated to become 78. So most of the gases, they will turn into ethanol. Okay. And and when it goes through the fractionating column, it will make sure that it's only pure ethanol. It's most of the gas is going to be ethanol. It's not exactly going to be pure. As I said, water, the gases are random. So there might be a little bit water inside the ethanol depending on the capacity, but most of the ethanol will come out and most of the water will stay here. Okay. Paper chromatography can be used to separate a variety of mixtures. Okay, blah blah blah, blah blah blah. Okay, we're gonna do an experiment using ink and food colorings. And most inks and food colorings are not just made up of one color but contains a mixture of dyes. Okay, so in paper chromatography, although you only see one color, once you go through the chromatography, you will see different dyes, and these different dye colors mix together and form one color. It can be used to separate a mixture of colorless substances such as sugars, but then some method must be used to make the spots visible on the paper. Okay. So let me explain what this is about real quick. Okay. See the pencil line. Okay. You dip this paper on this pencil line, and this is the level of the water. Okay. When I say water, I mean the solution. And the solution, of course, has many different elements. It has the solvent, which is usually the water, and different types of dyes. Okay. And D1 is simply D1 is simply the blue dye. D2 is the purple dye. D3 is another type of purple dye. D4 is the orange dye. So you mark the dye here, and M is just a commercial food coloring that we're going to dissect. Okay. And then we put this all in water, and because it's in water, the paper will soak and the water will continue to go up. Look at the mouse cursor. As time goes by, water will keep going up, and so is the inks. So are the inks. Their blue inks going to keep go up, purple inks are going to go up, and the orange ink is going to go up. But they travel at different speeds. Excuse me. They're going to travel at different speeds, and water obviously is going to be traveling the fastest. And at that exact time of ending, you will stop. You will take this out of the water solution, and you will see that this side is wet and this side is dry, meaning water traveled this much. If you look at y, this is how much water traveled after some amount of time. And x is how much this purple ink traveled at the same amount of time. Okay? And this separation happens because it travels, the ink travels, the water travels at different speed on the chromatography paper. Okay. And using the difference in speed or using the difference in the distance traveled, we can figure out what ink exists in this commercial food coloring. Okay. D1, D2, D3, D4 are the reference points, and this is the one we want to figure out. Okay. Okay, going through, the mixture M has spots corresponding to dyes 1 and 3 and 4. They have the same color as the spots in the mixture. Okay, let's go through this. Okay, this is basically the solution, analyzation of what is going on. Okay, I said D1, D2, D3, D4 are reference points. D1 is how the blue dye travels, D2, purple dye travels, D3, purple dye number 2, this is how purple dye number 2 travels, D4, how orange dye travels. These are the reference points, and M is a food ink that we're going to experiment with. And in the end, you see purple dot, blue dot, orange dot, and you can tell that okay, this commercial this commercial dye contains D3 dye, D1 dye, and D4 dye because you see these three ink blots. Can you say D2 exists in this ink blot? No, because it doesn't exist. They have the same color as spots in the mixture and have traveled the same distance on the paper. Although dye D2 is the same color as one of the spots in the mixture, it has traveled a different distance and so must be a different compound. Sorry, mistake. No, I didn't make any mistakes. Although they're the same color, the difference in the distance traveled and the fact that it doesn't exist here, it shows that D2 does not exist here. I already explained this, I'm just double explaining it. Instead of just saying the spots move different distances, we can use the RF value to explain how far the spots move. RF stands for retardation factor. Each time we do a chromatography experiment, the solvent will move different distances along the paper. This means we can't just report the distance moved by a particular spot, so we have to work out a ratio instead. What this is saying is when we do this experiment multiple times, maybe the time we put this paper in the water, maybe it's different. Sometimes you put the paper in for 1 minute, sometimes you put it in for 10 minutes, sometimes you put it in for 30 seconds. It's all different. So you can't just say, okay, so this is 10 centimeters, this is 5 centimeters. So if this ink blot has 10 centimeters traveled, then it means this ink is from company A. This ink is from company B. We cannot identify the ink blot based on this distance alone. We need to find the retardation factor. We need to find the ratio because the ratio stays all the same. Okay, even if you put 5 minutes in, 1 minute in, 10 minutes in, the ratio will stay the same if it's the same dye, if it's the same chemical. Okay. So you calculate the distance the solvent traveled, distance the water traveled, and you calculate the distance the ink blot traveled, and you divide them, x over y. And that's your retardation factor, RF. And this is going to be significant in your experiment. Okay. RF is the distance traveled by the spot over distance traveled by the solvent. Distance traveled by the spot, distance traveled by the solvent, x over y. Okay. And so from this we can figure out the retardation factor. Um, I won't go over this. Actually, let's go over this. Let's say this is 2 centimeters, and let's say this is 2.1 centimeters. The retardation factor would be 2 over 2.1. It's very close to 1. Let's calculate this one. Let's say this is 1 centimeter. Y is 2.1 centimeter. The retardation factor for D1 is 1 over 2.1. Let's say this is 0.8. This is 2.1. Retardation factor for D2 is um, 0.8 over 2.1. And same thing goes on. You need to calculate the distance between the pencil line, the line where you dip the paper inside the water, to how much the blot traveled, how much the solvent traveled. Okay. And this is just simply the calculated values. And this is the calculated values of the reference points. And simply after you get the value, you're going to compare and contrast and figure out which dye exists in um, each commercial dye. And you will go over this in your experiment. So don't worry too much if you didn't explain half of it. If you didn't understand, go on YouTube, search chromatography retardation factor GCSE. Search those keywords. These keywords, retardation factor, chromatography, GCSE, and just watch any videos that come up, and you will have those world-class teachers show you how to calculate the factors. Okay. And this is the end of the chapter. Let's go over the learning objectives, see how we understand how to classify a substance as an element, compound, or mixture. Okay. We need to look at the molecules. If we see different types of molecules exist, then it's a mixture. If we see the same type of molecules, then it's an element. Same type of compounds, sorry, same type of an element, it needs to be pure. Compound, it needs to have two or more different atoms. Carbon dioxide, water, they're compounds. Element, they're nitrogen, oxygen, they're elements. A mixture is simply a mix of either different elements or different compounds or mix of both. Second, understand that a pure substance has a fixed melting and boiling point, but that a mixture may melt or boil over a range of temperature. Okay, just just memorize this. Just memorize this example. If it's a salt water, melting point will be lower than 0 degrees. Boiling point will be higher than 100 degrees Celsius. Okay, it's gonna keep changing. If it's impure, it's gonna be further away from that 0 100 mark. If it's pure, it's going to be 0 and 100 exactly. That's all that is about this point. Describe these experimental techniques for the separation of mixtures. We talked about separation of mixture as physical means. Okay, separating the compound, separating carbon dioxide, separating carbon and oxygen from carbon dioxide, that's a chemical means. It's very difficult. The separation of mixture in by physical means, it's easier. Simple distillation, fractional distillation, we use different boiling points. Filtration, we use the particle size, and we also use how it's soluble in water. Okay. Crystallization uses the boiling point change. After you evaporate all the liquids, you will be left with crystallized salts. Paper chromatography uses different speed when traveling along the chromatography paper, right? Usually, water travels the fastest. Water reaches this point. Purple plot changes. Purple plot traveled this much. Blue one traveled this much. Orange one traveled this much. Meaning the orange ones move slowest. Water travel fastest. Okay. Okay. And using these different speed and calculating that retardation factor, calculating that ratio, we can identify the components of a mixture. And later in this class, we will do an experiment using paper chromatography. Okay. This is the end of chapter, and let's move on to doing paper chromatography experiment. And first, we will be watching a simple YouTube video on paper chromatography, and then we will do the experiment